Hi, I'm Dave, and I'm nicking nine near.
Welcome back to the ESP32 sampler, part 7. Feels like a never-ending project, doesn't it? Anyways, what are we doing today? Well, we've got a new microphone in hopes that we improve the clarity of audio that we are recording into our sampler. Because the old one, if you remember, didn't sound that great. We're hoping that this one is a little bit better. And you say, Dave, what module did you end up buying, bud? Well, I got a very simple Electret microphone module. It is called the MAX9814 Electret microphone module. This microphone module, it's optimized for the spoken word, apparently. So the cool thing about this little module is it's got a preamp built into it with adjustable gain stages. It's got DC offset already at 1.25 volts. It has an output range of 2 volts peak to peak max, which is perfect for our application here. So it's super simple to hook up. In fact, it's basically the same as the last module. GND gets hooked up to ground, VDD gets tied to 3.3 volts, out goes to GPIO 36, and gain, well, we're gonna start at the lowest gain setting. So we're gonna start at 40 decibels, so we're gonna tie it to 3.3 volts. It's that simple. Let's try it out with the code as we have it and see if we get any noticeable difference in the quality. So we've got our little guitar amp hooked up, got our sampler hooked up, we have our sketch on the ESP32. Let's record the spoken word and see if it sounds any better than it did before. Let's check it out. Hello. The nice thing about this new module is that I don't have to shout into the microphone. Before I had to yell into that microphone module to get it to register anything. So it's nice that I don't have to yell. I can speak with normal inflection and normal tone. It's still not great. Now, there's a lot of reasons for that. There are potential issues with the analog to digital converter. Now, I'm gonna try to explain this. It's not gonna sound good, but I'm gonna do my best. Close your eyes with me. In your mind, picture a perfect sine wave, and you want to capture that sine wave, right? Now, in an audio optimized linear analog to digital converter, you'd get a nice smooth capture of the waveform. With the ESP32's analog to digital converter, it's non-linear, okay? What that means is that as we're capturing the waveform, we're getting steps in between each voltage jump. It's not smooth, it's like a step. So that's why we're getting that real crunchy, kind of non-clear audio, but you still get the inflection of the tone. So we might have to change the analog to digital converter on this, and there's a whole bag of worms that comes with that. With that said, there are some things on the software side that we can do to try to improve this setup as it is. I'm not convinced that it's going to clean it up 100%, but let's jump into the code, we'll make a few changes and see if it just does anything. One of the things that we can do to improve the audio in our sampler here is we can actually configure the ADC at a very low level, which means we're able to get cleaner and more accurate digital readings from our microphone. So in order to do that, we need a library called adc.h, and we include that right at the top of our sketch. The next part we need is in setup. So the first line is going to set the bit rate to 12. So it's going to set our output range from 0 to 4095. Now, in our previous sketch, we didn't do this. So in practice, when you're actually doing that sampling without this setting, you're not getting the full range of the ADC. And then we set a little bit of attenuation, this analog set attenuation line. It's giving us 11 decibels of basically headroom to record our samples, okay? Next, we're going to jump down to record audio. In the record audio function, we're going to be looking at DC offset. Now, the DC offset happens when a signal doesn't oscillate evenly around the center of the DAC range. For our ESP32, should be approximately 128. That should be our center, okay? If there's a DC offset, what happens is that instead of the waveform swinging around 128, it might actually hover a little bit higher or lower, say 160, 120, 100. So if that actually is happening in our sampler, it's going to reduce the headroom that we have for recording. It's going to add distortion, and it's going to give us a lot of unwanted clicks and stuff within the audio sample. So the next couple things we're going to do is we're going to actually try to take that away. We're going to reduce that as much as possible. So in step 1, we're recording the audio in the exact same way we did in our previous sketch. The difference this time is that we're adding a safety check in to make sure that our recorded value is constrained from 0 to 495 before we downshift it, okay? Step 2, we're going to compute the average of the samples, right? So we're gonna sum all the samples to get a total and divide by the total of number of samples to get the mean value. And this average is going to represent our DC bias. So how far that signal has actually shifted from 0. And step 3, we're going to remove the DC offset and recenter it around 128. How we do that? We subtract the average from the sample, centering the waveform around 0. We add 128 to shift the 0-centered signal back into the 8-bit unsigned range of 0 to 255. Then we clamp our values, making sure that they don't go below 1 and they don't go above 255. What this is going to do is it's going to reduce distortion caused by the signal that is not centered at 0. And then finally, so this last step, so we're going to take a sample, not the first sample or the last sample, but all the samples in between. We're going to average each sample with its neighbors, producing a low-pass filter. This is going to reduce high-frequency noise and harsh crunchiness in the output. We've got our new sketch with our optimized code. Let's see if it's actually better than previous. Hello? 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 All right, well, that didn't make a ton of difference to my ears anyway. But it's good to have in the code, I guess, you know. Yeah. But there are 2 roads that we can go down here at this point. We can just get this thing done by saying, hey, the sound is the sound, and get it finished and move on to the next thing. Wink, wink, nudge, nudge. V2, ESP1200. Or we could go down the other route, which will take longer, and we will probably get a new ADC. But that comes with sacrifices. We'll probably have to give up some of our push buttons. I don't know. I don't know what to do. You let me know what you think. What should I do? Drop a comment below. I would love to hear from you. Let me know. Should we just get this thing done and move on to the next thing? Or should we try to improve the audio clarity? Which is going to take longer, but the project will still get done. So yeah, next week, I'm thinking we're going to tackle MIDI, try and get that MIDI stuff sorted out, unless there is an overwhelming response telling me to get a new ADC and go down that route. Anyways, if you like what I'm doing here, please subscribe to the channel. If you've subscribed already, thank you very much. That's it. Thanks for watching, and I'll see you in the next video.